Hello, everyone. I'm happy to welcome you to this very last SIPTA seminars of this academic year. And so Jeremy will talk to us about outer probabilities measures there and their updating. Without further ado, to close this academic year session of the SIPTA seminars, I will let Michele introduce Jeremy in more detail. So thank you, Jeremy, for giving this talk. And Michele, the floor is yours.
Thank you very much. Thank you very much, Sebastian. And it's a great pleasure to introduce Jeremy, who not only is a good friend, but is also a very distinguished scholar, in my opinion. He works at the intersection, as you can imagine from the title of the talk, at the intersection of statistics and imprecise probabilities, and in particular in possibility theory. And he contributed some very fundamental results and research. Among his accomplishments that are too many to list, there are the last two grants he told me he was able to secure were the Singapore National Environment Agency and the Ministry of Digital Development and Information, and also he's an editor of statistics and computing. Um, Once again, I really don't want to steal any more time to you. So, Jeremy, thank you very much for your time today, and please, the floor is yours.
Well, thank you, Michele, for the kind introduction, and thank you, Sebastian, for the invitation to present. So yeah, I guess the topic is very much within the sort of SIPTA remit. It's true that so far I've kind of worked more kind of directly with statisticians. I think trying to sort of push those ideas in mainstream statistics. But yeah, it's great to sort of connect more with IP people and with the SIPTA community in particular. So yeah, I hope this will sort of generate some discussions at least, and yeah, I'm very happy to sort of explain more things. So if there's anything that I say that is unclear, feel free to say in the chat, and we'll try to address that in due time. And I look forward to the questions. So today, the title is "What should we update? Outer probability measures and learning from ignorance." So, and that's really going to be the sort of main question here. I would say I'm going to try to explain why, in my opinion, these outer probability measures that I'm going to introduce are interesting objects, and they are very closely related to upper probabilities and in particular upper expectations. I'll come back to that. But the take here is a little bit different, and basically one of the key ideas in the talk is that these objects, rather than being just one of the descriptive statistics or descriptive objects that we might want to consider when doing imprecise probability, in a particular context, I believe that these objects are actually the kind of primitive object, and I'll try to substantiate that. So yeah, let's go. I'll start with some review of possibility theory. So I know that a lot of you know possibility theory, but I'll try to present it in a way that make it clear what's my exact take on it. So I think a lot of the results I'll talk about are not necessarily my results, and they are sort of standard results in possibility theory. But I'll kind of take a particular direction that perhaps is not quite as usual, and so I'll give all the main steps there to be sure that everyone's on board. Then I'll talk about outer probability measures themselves. That's the kind of main object in this talk, and I'll conclude by discussing the role of these outer probability measures in IP and how they relate to existing things and how they're different. So usually I start my talks with some motivation about why we might want to do something else than just standard statistical theory, standard probability theory. So for this crowd, I'm going to assume that we kind of all agree that there's interests in exploring alternative ways of modeling uncertainty. And so I hope everyone's on board with that. And so I kind of motivate this in particular in my usual talks with some of the main topics with some references. So I didn't want to. I kind of threw away that standard introduction, but I didn't want to throw away the references. So I still put them all in a slide here. So of course, one of the main components in what I'm going to talk about today is possibility theory. So, and again, this is not a new topic, it's a topic that's been very well studied. I make some connections to inferential models as well, Dempster-Stefan theory, and at the end, of course, general IP. But I also wanted to mention some related topics. I'm not really going to go in those directions today, but those are sort of directions that are related to outer probability measures as well. And so in particular, the sort of more machine learning aspect of imprecise probability, which I also work in, some fiduciary inference. And actually, I wanted to mention, this is kind of less well known, perhaps known in this for you guys, but so this kind of really max plus algebra version of things, and in particular the work of Del Morin, who sort of expressed this kind of idempotent probability and how it relates to optimization, etc. There's very interesting stuff there, and also some relation to large deviation theory. So this is kind of a very general thing. Of course, I'm going to go more in details, but wanted to sort of draw the map of what's related. Okay, so let's get into the math of possibility theory. So here, the main thing is that we are interested in modeling the information about one fixed parameter. So this is, I would say, it's quite a different starting point from standard IP, as I understand it. So we're not really thinking in terms of betting prices. So we're really starting from epistemic uncertainty, trying to model that epistemic uncertainty in a way that's more dedicated to its particular form. So of course, the usual thing is just to throw a probability at it. And but here we're not going to do this, and we're going to think in terms of how do we actually model the epistemic uncertainty about this fixed parameter. So generally, I try to follow the probabilistic route as much as possible, because that makes it a lot easier to reuse results there and to kind of not have to reinvent everything all the time. And so for this, it's actually quite convenient to think in terms of basically think objects like random variables, but adapted to this context. And so, and this notion of uncertain variable exists in the literature, so this is not new. But basically, the way I see it here is that we have sample space in which there's a true outcome, that's the true state of nature, and all the other outcomes in that sample space are possible states of nature. And so, and this uncertain variable, and deterministic because this is just for epistemic uncertainty, basically takes state of nature and gives us the corresponding value of the parameter for that state of nature. And so in particular, if we start from the true state of nature, we get the true value of the parameter. So, and there's no probabilistic structure here. I don't need to equate omega u with any sigma algebra, or I can just think of the basically the trivial, not the trivial sigma algebra, basically the 2 power omega u as my sigma algebra, and that's fine. So something important here. So we have we want to describe the information that we have about that uncertain variable, and describing here is a very important word. As opposed to probability theory, we don't have a single probability distribution that we deduce from the random variable. We have some uncertainty about theta, and we describe it with a possibility function. And so for that possibility function, we still have non-negativity, but instead of integrating to 1, we have suprema 1. So one interpretation of it that's going to be useful later on in the talk is to think of F as some sort of odd ratios, and that, I think that helps with interpretation as well. So because if theta star is the argmax, I'm not going to focus too much on the mathematical formality. So actually, most of the time, I assume the supremum is attained, and so basically all the subs are maximum if we want. That's not really what I want to focus on. So let's say we have a theta star that's in the argmax of f theta, is the mode basically. Then the function evaluated at theta star is equal to 1. And so this is a very obvious equality. It's not really, there's nothing deep here, but it does tell us that the possibility is basically how likely is theta compared to theta star, compared to our best guess, which is the mode. I'll come back to why that's the case. So that's how we can think of a possibility function. And in particular, something that we gain straight away is that if we want to say that we know nothing, we can take the function that's equal to 1 everywhere. And this is always proper as a possibility function because we only assume that the supremum or the maximum is 1. And so this is actually something that's very difficult to do in the probabilistic case, to say that we know nothing. And that's actually a kind of an open problem in probability. So here's actually the simplest thing that we can do, and that's great. So not unusual for imprecise probability, but I think worth pointing out. So perhaps one thing that I do slightly differently, so I really try to follow the usual probabilistic route. And so in particular, the sort of main possibility function, the one that always comes up, that's the simplest to deal with, outside of the one that the function that's 1 everywhere, is the normal possibility function. And so at the moment, it looks kind of lazy. I just renormalized a normal distribution, multivariate normal distribution, and I get a function that has maximum 1. It's a valid possibility function. So of course, right now, it doesn't say that it's a very fundamental object, but what we'll see is that actually this is as important as the normal distribution in probability. So for instance, if we decide to do a change of variable formula, so that's the kind of standard way of writing a change of variable formula in possibility theory, then what we can prove very easily that if the mapping is linear, so it's matrix multiplication here, we're in a multivariate case, then the transform uncertain variable is going to be described by the usual, a normal possibility function with the usual expected value and the usual variance. So these are very easy properties to prove, but actually most of the properties of the normal distribution can just be imported into possibility theory, and so it makes the normal possibility function very important. So this is just an example of what we can do beyond saying that we know nothing, and that's actually this is just as easy to, for instance, if we're eliciting a prior, we can just say, well, my best guess is mu, and that's how sure I am about this guess. And that's just as easy as doing it with a probability. So we're not really, in most of the stuff, this kind of basic approach to possibility theory, we don't really have to do anything different from what we do when we do standard statistics. But now we just thinking about the parameter as being something non-random, very similarly to frequency statistics, and there are connections there as well. Okay, so let's look at some properties. So we cannot sample directly from a possibility function. We decided to model epistemic uncertainty rather than aleatoric uncertainty. So we have to give up sampling, and that's fine. That's how it works. And maybe that's the right time to say, although I'm going to emphasize the nice properties of possibility theory, this is not to say that it's better in any sense than probability theory. I think it's better at modeling epistemic uncertainty, but if what you have is a random phenomenon, then use probability, of course. So this is not to say that this one is better than the other. And actually, the principle with these outer probability measures that I already mentioned is that we're going to combine probabilistic and possibilistic object to get a much richer representation of uncertainty. So that's, but I'm going to define this properly later on. So just on the last slide, I define a normal possibility function. So if multivariate normal in particular, so if we think of, for instance, the bivariate case, we have two components in our vector, and we have information that potentially is joined between those two components via the covariance matrix, just as in probability. So this, for instance, this joint possibility function here could just be a multivariate normal, and that would be perfectly fine. And so once we have these joint possibility functions, we can think about what it means to do the sort of usual operations that we do when we do inference, that is marginalization and conditioning. And so from that viewpoint, we can actually derive these results, but here I just present them as properties. So marginalization is going to take a supremum of that joint possibility function, and conditioning is going to be dividing the joint by the marginal. So this is exactly like in probability, and here we just replace the integral by supremum. Similarly, we have notions of independence. So I think the most fundamental one is the one that can be expressed as a product. So the way I see it is that's what we think about when we say that we have independent reviewers on a paper. Their source of information are disjoint. And so we can think of independence without thinking of randomness. And for instance, in some of the literature, people use the minimum to express, to kind of combine basically marginal possibility functions instead of using the product. But actually the minimum, I don't see it as something as fundamental, because it can actually be recovered if we define some sort of meta possibility function that says, I don't know, I have a joint possibility function, but I don't know the correlation. I don't know the what's the correlation between the two components, and we marginalize everything. Basically, we get the minimum. And so I think the product is more fundamentals, and I'm going to focus on that. And so one important thing that's, again, not unusual for people who do imprecise probability, we can combine information, but that's still just Bayesian conditioning. So here I've defined what conditioning is, and here I'm conditioning on the fact that I have two uncertain variables, and that in fact these two uncertain variables, they represent the same unknown. And when I do this, it just gives me the joint evaluated on the diagonal, renormalized. That's because that's a conditioning. So I didn't really have to define anything here. It just follows from that definition. And so that's going to be useful later on. And if we think in terms of information, it's not surprising that we can easily combine information. Writing this with P probability mass function is fine, but writing it with PDS, with probability density functions, can be actually quite tricky. And here there's no issues because those functions are not densities. And so we can just evaluate everything pointwise and we'll be fine. And one last point is that functions are not unique. So we can change a function. In particular, we can, if we have a possibility function and we decide that has maximum 1, and we decide to define another possibility function that is larger pointwise, then we have not changed. We have lost information, but we've not introduced any spurious information, and that's actually a very convenient thing to do. So here at first I say that can be seen as a drawback. It's a little bit unsettling that the possibility function is not unique, but it's actually very convenient. And in particular, this tells us that we have a partial order on the set of possibility function, and that, again, the structure that is going to be convenient later on. Okay, so moving on to proper Bayesian inference. So I've written Bayes' rule in a very specific way, so that I don't have to say here whether those pi's are probability distributions or possibility function. This is Bayes' rule that's kind of true for both. Whereas the likelihood, I'm going to reuse the term prior and posterior for these objects, whether they are probability or possibility functions. And so the main difference is that the evidence, or the marginal likelihood, is not written in the same way. It's going to be a suprema in the possibility case, and that has actually quite a lot of consequences. But yeah, I'm actually not going to focus too much on that in this talk. Right, so here again, I'm presenting possibility theory in that specific way so that it will make sense later on when we combine it with probability. So I don't want to focus too much on possibility theory. All right, and so here I'm really just a very high level slide to say that a lot of the nice properties of Bayes' rule and the ways in which it can be recovered in some basically axiomatic way. This is true. So these are results that show that Bayes' rule or some loss-based version of Bayes' rule can be recovered from principles, or from this information processing rule, or from given axioms. And so this is true for probabilities. This what those papers are about. And for instance, we've shown that the same principles, just adapted slightly, will give you the possibilistic Bayes' rule instead. And so a lot of that motivation that behind Bayesian inference actually just continues to be true. It continues to be relevant for possibility functions. And so in particular, something that I would just like to highlight a little bit is that for probability, if we want to think in terms of the information that's carried by a probability distribution, that's well defined. That's what information theory is about. But we typically have to reduce to a scalar. We have this for one probability, we have one scalar that tells us how informative that distribution is. For a possibility function, because we are already modeling information, we can just think in terms of, it's more of a functional thing. So we take minus log of our possibility function. And so 1, which tells us we know nothing in the sort of information scale with the minus log is going to give us a 0, indeed, 0 information. And when the possibility is 0, then on the information scale, we have infinity. And indeed, knowing that something is impossible is something that is very strong, and that corresponds to the infinity in log scale. So, and actually, in that information processing rule sort of viewpoint, we that gives us actually some nice quantities to work with, and we kind of avoid some of the paradoxes there. Well, not paradoxes, but kind of limitations, I would say. Okay, I'm not going to go into details here to not get too sidetracked. So, but you could ask at this point, and of course that's perhaps one of the most obvious limitations of trying to follow probability theory as closely as possible, is that we've so far I've shown you that we can do a lot of the same things, and so then where do we get the benefits? What's the point of doing it if we just have the same properties? And so one of the most obvious advantages is, I already mentioned, that we can say that we know nothing, and actually that fairly directly addresses the problem of defining what objective Bayesian inference means. So the usual criteria for objective Bayesian inference is that the prior should be proper, it should satisfy the likelihood principle, it should be invariant under reparametrization, and ideally coherent under partitioning. So basically, it's a little bit stronger than this reparametrization, even if we don't have a one-to-one mapping, or if we actually have just kind of a binary relation between two spaces, everything should still be coherent. And so this is very hard in probability. Things like Jeffreys prior will be invariant in the reparametrization and will fail everything else. So you try to satisfy one, you lose everything else in probability, basically. So, but here we have a very natural candidate, that function that's one everywhere. And so it is proper as a possibility function, and it obviously satisfies the likelihood principle. It doesn't depend on the likelihood. And if we remember our change of variable formula, we just had supremum of the possibility function with no Jacobian, because those objects are not densities. So it's actually invariant under reparametrization. Whatever mapping I apply to my uncertain variable, if I knew nothing about theta, I still know nothing about t of theta. And so at least in the image of t, but again, I don't want to go into the sort of mathematical details here. And actually, this is also coherent under partitioning. So even if I transform through the inverse of a mapping, that is still going to behave in the correct way. And so, of course, this doesn't mean that we have to use one all the time. We can actually use, that can be just for one component. We can use informative possibilistic prior for other components. And what we'll see later on is we can even use probability distribution for other components if we believe that they are well modeled by probability theory. And what we've partially shown in this paper, and we're kind of further working on this, is to show that it addresses the marginalization paradoxes that were identified by Philip David. And so, and those things are what arises when you try to use improper priors in probability. You have those paradoxes that basically, depending on how exactly you formulate your problem, although those things should be equivalent, you get different results. And that's, of course, statistically, that's an issue. So this is avoided if we use this prior, mainly because it's proper, but of course, to show that it's indeed the case is non-trivial and is interesting. So at this point, of course, we could say that we still have something that is subjective. So we just have this posterior possibility function, and maybe we don't really know what to do with it. It's not going to have necessarily good frequentist properties. Sometimes might not be too bad, but there's no guarantee in this form. And so yeah, that's the question. What do I do with it? And so that's where the work of Ryan Martin has been extremely interesting to me. So because what he advocates is that this posterior, what I would consider as a posterior possibility function, it can be validified. So as to, and now we have the result of this is another possibility function. So we don't even leave the possibilistic framework. So we get this other possibility function, which now has strong frequentist properties, in particular is strongly valid. And we don't, in in some way we can extend to informative prior, but it's a bit more complicated. So I think that's a really interesting result that shows that there's something quite fundamental with these objects and with possibility theory in general. So, and actually this is the first example of a principle that we'll see again later on, which is that first we are going to work with these possibilistic principles to condition, to marginalize, to do all those operations according to possibility theory. And then at the end, as a final stage, we're going to validify. And that's, I believe that's what Ryan Martin advocates for as well. But that's going to come back again. First, we do all the operations that we're interested in. And at the end, if we want frequencies properties, we obtain them by validification, but not before that. And so now we have, let's say we have either our row posterior and just the Bayesian posterior, or we have our validified object. And there's a question of what are the statistics? How do we work with it, especially for the row posterior? So, and it was not entirely clear to me what was the sort of nicest way of defining expected value and variance. So with my co-authors, we took sort of the problem the other way around, and we sort of worked on law of large numbers and central limit theorems, and basically just to see what those limits are. And so the law of large number typically gives us a notion of expected value. And in this case, we have the sort of core object here is the mode of the possibility function in question. And so that's actually already quite natural. I mean, and the mode obviously is already a very standard statistic to use in probability theory. But the difference is that here the mode has excellent properties. So in particular, similarly to the MLE, and that's unsurprising, we have these kind of results where we can map the mode through any nonlinear mapping, and that's going to be coherent. And so, and this is really interesting, and this is not true for the mode of a probability distribution, again, because of the Jacobian interchangeable variable formula. So, so I think that's here we have a very strong notion of modes. So if we decide to change parameterization, our mode is going to be consistent. And so same thing for the CLT. Typically, we kind of get a notion of variance there. And so here, what we see first, we recover our normal possibility function, and the variance of this limiting possibility function is the inverse of this notion of precision. And actually, you might recognize something that looks like the Fisher information, and actually we can, in the limit, we do get something that is exactly the Fisher information. But here is a slightly more primitive object where we are just saying, let's look at the curvature of our possibility function. And again, actually, we see our minus log here, which relates to information, so it's unsurprising. And we're going to look at the curvature of that object. And actually, this expected value here, because of that property, it can also be pushed inside here. And so this object is just the curvature at the mode. And so with the mode and the curvature at the mode, in the standard way, this would be a Gaussian or a Laplace approximation. Here, it's actually moment matching. So so we get some nice explanations for methods that are very standard. Okay, and so this is my last slide on pure possibility theory. So we've done quite a lot with this. So we have a recent paper where we do some form of causal inference with instrumental variables. I have some papers on basically information fusion, federated learning, where we show that we can do Bayes row in a distributed way while preserving optimality, which is not possible in the probabilistic case. And so this ongoing work on prior specification and addressing those marginalization paradoxes that I mentioned, and as well as variational inference, this was kind of needed because again we don't have sampling in a native way, so we need other approximation methods, and so variational inference was a natural one, and it turns out actually it's a very interesting direction as well. Okay, so, all right, let's move on to these outer probability measures that I've mentioned several times. So the idea here is to say, well, now we have something that models epistemic uncertainty. And again, actually, I've not said that. So the idea here is that the possibility function models epistemic uncertainty directly. I don't really think of it as, at least not in a primitive way, as being some sort of upper bound through the corresponding measure as an upper bound that would define a cradle set. Here, I really think of the function as the primitive object. And so again, it's not really, I don't think of it as an upper bound. I think of it as the object that we're going to work with. And so that's why actually I should have said that earlier. When I write Bayes rule, I don't have kind of some sort of upper bound divided by a lower bound sort of structure, because the possibility function in that context is not natively an upper bound. It's just the object of inference. And so in that context, it makes sense to have a ratio between a possibility function and itself, because that's not seen as an upper bound in those operations. So let's continue with that. We have this kind of hopefully natural model for epistemic uncertainty. And of course, we have a nice model of aleatoric uncertainty through standard probability. So the question is, how do we combine those things? Because not everything is epistemic, not everything is aleatoric. We have both in nature, or we need both in statistical inference. And so, so how do we combine those things? So, well, to define again, some sort of notion of random variable is pretty easy. I'm going to say an uncertain variable takes both the unknown state of the world and all the random phenomenon in the world as an argument, and gives us the value of interest as an output. And so here in this case, for the random part of things, I do have probabilistic structure, which in general is going to be conditioned on omega. The randomness is allowed to depend on things that are fixed in the world. So that's fine, I can write it, but what can I do with it? And actually typically in probability, in general, we try to make the sample space disappear as quickly as possible, because potentially that's a very large object that we don't want to deal with directly. But here it's not so obvious, because if I just fix omega u, this object becomes a random variable. I could deduce the law of that random variable, but potentially both the variable and the distribution, the underlying probability depend on omega u. And so I'm going to have a distribution for x that is going to depend on omega u. I don't want that. I want the whole sample space to disappear. And so I have no choice but to introduce additional structure. And so there are the two simplest way of doing that, or two, I would say, simplest yet non-trivial ways of doing that, is to assume that first I have a deterministic uncertain variable that takes only the states of the world and gives me the corresponding parameter. And then I have another object that takes that parameter and gives me the corresponding randomness. Or I could do the other way around. I could say first I have a random experiment, and based on that random experiment, I have some deterministic thing that happened. And so, for instance, I'm going to come back to this. This is just inference. I define a parameter, and then I have a random experiment based on that parameter. And this could be, I throw a dice, and then I have my adversary in the game who makes a decision based on the dice roll, which I don't know. So that would be, then the omega u would be kind of what is his policy, kind of on how to choose his next move. So those things make sense. But what we see here is that we've introduced actual structure in the space. We have no choice when we have these kind of alternating variables of alternating nature. We have no choice but to choose a direction. First theta, then y, or first x, then psi. And so, and that's really interesting, because that's, in this case, those are the simplest DAG you ever see, of course, well, almost simplest, but the direction here is not just wishful thinking. It's not saying, well, we think that it goes this way. It's an actual direction that we have to formulate in order to write things down. So, and actually this addresses some of the limitations of Dempster-Sheffer theory that were identified by Pearl, mostly actually because in this Dempster-Sheffer theory, what I'll show is that we basically belief functions are basically this. And so, and actually all of the limitations identified in this paper are due to not having this way around, basically. So once we have both, we can do this. And there are also some, this paper by German, which is kind of an interesting read, which claims to find some paradoxes in Dempster-Sheffer, and using this kind of structure, we show that those are actually not paradoxes. That's why I put paradoxes between brackets. Okay, so let's dig into it. So as I promised, we actually have belief functions when we first say we have a random variable, and then we have a deterministic uncertain variable, which depends So the variable itself and or its possibility function depend on x. And so, but here, if we think of f, for instance, as an indicator of a set, then this is really just a random set. But here we could think this is random fuzzy set if we wanted to. So therefore, those are correspond to belief functions. And so in this context, the one way to write the corresponding object is to say, so I'm going to explain this a little bit more in detail in a second. So we consider a test function that could be any function, any non-negative function with the right properties of our choice. And we have to respect the structure that we've defined. So first randomness, then deterministic uncertainty. So first we integrate, and then we take a supremum for the deterministic uncertainty with respect to that test function. So for instance, if we want to evaluate the likelihood of some event, we can take phi to be an indicator of that event. But phi, in general, we need phi also to potentially be arbitrary functions. And because this object is not additive, these things are not equivalent. Characterizing on functions or characterizing on sets, it's not the same thing. So we really have to use functions here. And so this is, you could say this is just an upper expectation, and that's true. But again, because the non-additivity or the sub-additivity in this expression is not really seen as being an upper bound, it's seen as being a sort of the genuine primitive representation of the deterministic uncertainty, the epistemic uncertainty that we have here, then again, this is the object of interest. It's not just an upper bound. Of course, we're still free to consider the cradle set that corresponds to it, but from this viewpoint, the primitive object is not the cradle set, it's the outer measure itself. And so in particular, these kind of outer measures, they satisfy that very trivially that if we give it the function 1, they're going to be equal to 1. And so that's why I call them outer probability measures. So, okay, I'm a Bayesian, as we would have guessed so far. So the first thing I'll do with this is to try to write Bayes' rule, to think of this as a joint representation of uncertainty and think about what Bayes' rule means. So let's say in this case, we roll the dice, and maybe we've actually not seen the dice roll. We don't have access to that information. However, we know we have some information on the strategy of our opponents, and we know the decision that they make. Then we can learn about what the dice roll was. So of course, that's not the only application, but why not, right? That's what it means here. And so that's our Bayes rule. It actually looks very much like the standard Bayes rule, because here both the prior and the posterior are probabilities, but now the likelihood is the possibility function. It's not very shocking. I mean, usually we don't really care about how the likelihood is renormalized. So not shocking, but yeah, we can write this, and we can, in general, use Bayes' rule of these objects in more complicated way as well. What's a lot more interesting here is that if we take two objects like that and we apply our fusion rule, so basically we take the joint between two objects like that and we condition on psi being equal to psi prime. So we have two versions now, and we condition on this. Basically, what this is going to give us, the corresponding posterior, is Dempster rule of combination. So from that viewpoint, if we accept this as a representation of uncertainty, then Dempster rule of combination is Bayes' rule. Bayes' rule apply to those objects. So let's go on. So now the other way around. So if we think that first we have a parameter and then we have a random experiment based on that parameter, that's really just inference, either frequentist or Bayesian at this point. And so again, we can write our outer probability measure with our test function, but this time we have supremum and integral. And so we see here again that of course the ordering between this operation is not exchangeable. And so again, that direction on our DAG is not just for intuition, right? It does matter for what kind of uncertainty we're going to have, and it does matter for the credibility of the events that we'll get out of them. So once again, I can write Bayes' rule, and this is actually the Bayes' rule that I sold you earlier, where the likelihood is a probability. And so again, this is well defined, and that's typically how I do possibility theory, where I still consider a random experiment, and the observations come from random experiments. So this is in line with standard statistics, but I swap the posterior for possibility function, and then the prior is a possibility function. So the posterior is also a possibility function, and we can do all sorts of things. In particular, we can deduce a Bernstein-von Mises theorem, which tells us that this object actually in the limit, asymptotically under assumption is going to give us a normal, again, the normal possibility function with the mode at the MLE and with the variance related to the Fisher information. The usual BVM, but this time for a possibility function. So again, the nice results of Bayesian inference, they just continue to apply here in this possibilistic setting. Okay, slightly more complicated, but it's quite important here. So as I promised, this is not just this kind of Bayes rule that we had on the previous slide, where it's really like the standard Bayes rule. We can look at a prior now that is, the whole prior is this kind of object, that's a joint object. And so I'm going to work just for the example as a with parameter first and then random variable. So that's the inference case. And so now we have a likelihood that depends on both the parameter and the observation, potentially. And so if we write Bayes rule for that object with that prior, what we get is actually, unsurprisingly, we get some sort of hierarchical Bayesian inference. And the very nice thing that happens here is that if I write this all in full, I'm going to find that under the integral, I have this object, which is just the conditional Bayesian posterior, standard Bayesian posterior. And then in front of the supremum, I have this updated possibility function, which is again just a posterior possibility function, but now with the marginal likelihood, as is standard for hierarchical Bayesian inference. So actually, this is very nice, and that's what's being said in the title here. So these, however complicated these OPMs are, this is just an example. Huh? I could stack up. If my DAG is more complicated, I'm going to have to stack up a lot more integral supremum. It's going to become a nightmare to compute, but it's possible. And what this shows is that those things are closed form under updating. So if by just updating, we're not making things more complicated. However, that's not true for prediction. If I have some sort of Markov kernel that is now a general outer measure, and I want to predict this, what happens to this system that is described by this, then I have, so this is, that's where I really need OPMs to be evaluated at test function, not just at events, because this is the only way I can write prediction in general here as the prior measuring the Markov kernel. And this gives us a new OPM, and this is well defined, there's no issue here. However, in general, that OPM is going to be more complicated because we are stacking up the complexity of Q bar and P bar. So only if both, if the last layer here is of the same nature as this one, then it's okay. But in all other cases, we're going to stack the complexity. But this is not surprising. It's just, I just want to say that we have to be careful with those things. All right. I think hopefully I'm doing okay with the time. So role in IP. So I sort of try to motivate this already, so I don't have too much work to do here. So when we do standard probability and standard statistics, we just assume that everything can be modeled by probability distributions. When we do IP, we are going to think of as that's. Please correct me if I'm wrong here. That the object of interest mostly is the cradle set. So we have, in a sense, we do have epistemic uncertainty on which probability is the correct one. That's a little bit like the inference case, but now it's the cradle set that is the object of interest, and I think that, and that's great, and that's actually the one thing to do if we start from, for instance, from lower provisions. If the only thing we know is lower provision, then working with the cradle set is the right thing to do. Is the only thing that we can do that is correct. However, my point here is to say that if we go the extract step and we actually do the entire modeling of the system, which we wouldn't have to do if we're just doing standard IP, if we really model the entire system and both its epistemic and its aleatoric component, then the object that we update becomes the OPM itself. And so that's what I believe. Of course, I'm very happy to discuss this. I don't claim to hold the truth. So just some questions. Why not a random set formulation? So it's true that, of course, we can see a possibility function as a membership function of a random set. However, this is only true when we evaluate sets. When we evaluate test functions, those things actually, they can start to be different. And so then you have to choose one. And so in this case, I'll choose the possibility, the sort of native possibilistic approach. Why not a lower probability? So I already motivated this. Actually, with those Bayes rule, we've recovered a lot of nice properties like this information processing rule. We see how Dempster rule is Bayes rule for the OPM itself. So if we want to think of it as an upper probability, that's fine. But that's so from that viewpoint, the upper probability is the kind of rat object to work with. And if, again, as a principle, if later on we want to deduce a necessity, then or a lower probability, then we can do this as a last step thing. So once we have done Bayes rule, we have done marginalization, everything we need. What's we want to think in terms of necessity, that's fine, but that's the last step thing. So, all right, so let's think in terms of coherence. So coherence in terms of that the object we're manipulating is going to be basically the supremum of an expectation of a critical set. So and so which, as you know very well, and as far as I understand, so is going to guard us against shear loss, but also additional properties. So here it's actually, if we work with this object, in general, is not going to be coherent because we have the grading that's introduced by the possibility function. Means that in particular, if we take our test function and we just add a constant, then that is not going to be just the outer measure plus the constant because of the grading. So that tells us several things. We can, if we want, we can sacrifice the grading and we can say, well, let's only keep the parameters that are likely enough. So thresholding our possibility function and considering all the parameters that a posteriori are likely enough. Of course, if we take epsilon equals 0, then we only keep the support. And that actually would be the only way to be coherent. That sort of, not the only way, but through this operation, the only way to be coherent that perfectly aligns with the inference that we've done. Of course, we can also take this object and consider the Choquet integral of it, and then we have something that is coherent. And again, same principle. We do all, from my viewpoint here, we do all the operations, we update, we marginalize, and at the end we want coherence. We consider Choquet. So, and in particular, one way to motivate this is to say that here we actually allowed to start from knowing nothing. So actually, again, the possibility function are not density, so I can actually consider my parameter to be infinite dimensional. There's no issue at all. So I can say I'm going to consider all probability measure on some given space. That space itself doesn't have to be finite. And so, I'm going to say that I know nothing at all about any of those probabilities. But if I go back, I should have planned this better. This posterior is still, even if f is equal to 1, is going to evaluate this marginal likelihood and see which probability is more likely than the others. And so as a result, we are going to get a posterior that's not the trivial posterior, that's not the vacuous one. So we are going to learn something. And so if we put this into Choquet, we do have information. Well, I believe that if we start up from the cradle set and the vacuous cradle set, and we update it through the generalized Bayes rule, then we only learn basically where the probabilities are completely impossible according to the likelihood, which again is exactly the case of taking epsilon equals 0 here. We only learn things that are completely impossible. So here I think that we pay the price of having to do extra modeling, but once we have done that extra modeling, we sort of reap the benefits by sort of having a very fine control over what information we have and what we do with that information. So yeah, again, first we define this kind of row posterior. If we want coherence, we go through Choquet or we go through this and we make it coherent. Okay, so very quickly on dilation, so in general, if possibility functions are odd ratios or likelihood ratios. And so if any of our inference changes what theta star is, that's going to give us dilation. Some of the possibility a posteriori will be larger than in the prior. But this is not surprising because it's a relative object. So we shouldn't really compare the prior and the posterior point-wise. So there is dilation. It doesn't occur if we start from knowing nothing, because in this case, we don't really change our mind because theta star actually is the whole set. So we refine what we know, but we don't change our mind. So there's no dilation. And I think dilation actually is not really the most interesting property in this context. And it actually doesn't marry very well with with Bayesian updating. Basically, depending on how you do your Bayes update, you get different dilations, which shouldn't be the case. I mean, from a Bayesian viewpoint, things should be independent to the order of update, for instance. So And again, we have Benjamin says that guarantees that asymptotically, at least we go to the right parameter with the Fisher information. And so even if there's dilation in the process, I think that shouldn't be too much of a worry here. So yeah, it's basically my last slide. Now we want to exploit that structure of the outer probability measure. So with my team, we're looking into causal inference. I've not talked about them. We have some possibilistic exponential families, which we use to do variational inference. And so they have very interesting information geometric properties that we're looking at. There's some very natural application in extreme events. I think that's not surprising from an IP viewpoint. And that's it. Thank you very much.